Okay, so let's have a look at a solenoid in profile. Actually, I want to do this twice. Imagine I take a solenoid and I cut it down its axis. If I slice the solenoid down its axis, I would see the ends of the copper wire on the top and the ends of the copper wire on the bottom. I hope you can visualize that. Imagine if I cut straight down the center there with a bandsaw. What I would see is the ends of the wires up here and the ends of the wires at the bottom also. If I then give a direction of the current, you remember this notation, into the paper, into the page there, and out of the page here. And then by the right-hand rule, yes. By the right-hand rule, I can say that the magnetic field looks like this. Is that right? Oh, yeah, I got it right, haven't I? Right hand. Uh, Somebody else want to say that I'm right? Coming out of the board, it goes this way. That's right. That's right, isn't it? Out of the board, right-hand rule, that's easier to do. Out of the board. The magnetic field looks something like this. And if I draw it, you see a trend inside this solenoid, because this area in here is inside that length of that tube there that is encased by wire. The magnetic field will tend to do this sort of thing. Oh, not really that. It'll tend to move from the right to the left. And then outside the solenoid, it will want to do this sort of thing. Outside the solenoid. It'll want to do this sort of thing. And it will continue doing that. Something like the shape of a bar magnet. Okay, we know that bar magnets look, actually I'll do those ones right around. Something like that. And then off that way and off that way. We know the direction, of course, continues on as if it's doing some sort of a circuit. Okay. I hope everybody can picture that. And I know that inside the solenoid, because we can treat it like a bar magnet, then inside the solenoid is like inside the bar magnet. And so I would say south to north inside. And so I'll draw that. I'll say that this side is the south side and this side is the north side, like a bar magnet. The magnetic field travels south to north inside and north to south outside the magnet. Okay. And this device is called a solenoid. Solenoids. This is true of solenoids. The field around a solenoid is like that of a bar magnet. The field inside a solenoid is very close to uniform. The field inside is directed from south to north. The field lines outside occur as loops. Okay, I don't need to redraw that, I don't think. Let's have a look at some bar magnets here. Two situations. This picture will be clear shortly, not quite yet. I want to confuse myself. I'm going to draw the north side as red all the time. I find that easiest to remember. To have a convention is a good thing. So this is going to be north, this is north, and this is south. As if I've got bar magnets very close to each other. Of course, we know that if we brought the north end of a bar magnet up toward the south end of another bar magnet, then we would have a attraction between them. We know that there would be a magnetic field here in between them. So I'll draw that magnetic field. I'll draw it. It'll be reasonably uniform. Yeah. All right. Let me try again. All right. I'm just going to go with this, even though they're not perfect. Okay. And we would know because south to north inside, north to south outside, the magnetic field is directed up the page, of course. And I could put a current carrying wire in there. Or I could put a piece of wire in there. You can imagine the wires coming from us and going into the page. So we're just seeing the end of that wire sliced. If there's no current in that wire, what will happen to the wire? Nothing. It can sit in that magnetic field without being bothered whatsoever. What if I put that wire in this magnetic field? Here's situation number 2. And I say that the current is going into the page and it has a current. What will happen? Very simply, you could just say that that wire will experience a force. Why will that wire experience a force? I'm going to draw the magnetic field now. We know the magnetic field around the wire is actually in, yeah, that direction, isn't it? Okay. Magnetic field around the wire goes like that. The magnetic field, due to the north and south magnets, because magnetic field lines can't cross, we have this sort of thing happening. Oh, that's not going to work. I'll do this. Something like this. Magnetic field lines won't cross. These magnetic fields will interact with each other. Okay, and so we're going to experience a force, or that wire will experience a force. The magnets will experience the same force, but of course they've got large mass compared to that wire, so they're not going to want to go anywhere. Does anybody know in which direction the force on that wire is, and how you know? I'm trying to draw the arrows as neatly as I can, but it's getting a bit busy up that end. It is to the right. Correct me if I'm wrong. I do make mistakes sometimes because I'm always using my right hand, but sometimes I picture it wrong. You have to double check yourself. At the moment, I'm pointing my thumb in the direction of that current carrying wire into the board, and I'm got my fingers in the direction of the magnetic field, that external magnetic field. And if I look at the direction of my palm, if there were an arrow coming out of my palm, we would see the force on that wire is to the right. And this is where so I'll draw that force on that. This is the force on that current carrying wire. Looks like, well, it has this direction. And this is where we have the right hand palm rule. Right hand palm rule. Hi. Good, that's all right. Yeah. Yes, there is. Hand palm rule. Okay. This is where we take the right hand rule and we make it 3 dimensions. A little bit more complicated, not so bad. I'll describe the situation that's occurring here firstly, or I'll write it down so that you guys, when you come and look at it later, you will understand what's going on. Here we have a current in the wire. Which is going into the board, into the page or into the board. You guys would say into the page. The magnetic field due to the current carrying wire interacts with the external magnetic field. And when I say external magnetic field, I mean this magnetic field due to these permanent bar magnets on the outside. Let's move that up. On this side, I'll say no current in the wire. Therefore, no force. The force on the wire, current carrying wire, is to the right. Here is this. I'll put it back in a second. Let me just take a picture. I can't draw this very well, so I'll just cut this out. Here's the right-hand palm rule. Make it a bit smaller so it fits in there. If I point my thumb in the direction of the current as before, I point my fingers in the direction of the external magnetic field, then the force that this current carrying wire experiences is out of the palm. The question is, why is it like this? You might recognize, please, you might recognize something here that to do with the orientation of, let's have a look at the current. Now the current is approximately off in this direction. Okay. You'll notice that the magnetic field is in fact at right angles to it, or thereabouts. And the force is at right angles to both. Now I can't draw that very well. Yeah, all right, laugh. All right, so, but there's my current, there's my magnetic field, and there, current, magnetic field, force, each at right angles to each other. I, B, F. I'm not going to do that because I'll make a mess. Yeah, you can do this also, yeah. You think that's easy? Yeah. If that's easier for you, yeah, use that. And that is by having like a trigger finger and then putting one finger out to the left of that. That gives you 3 dimensions there also. The text teaches the palm rule, and so that's why I go with the text. That's the only reason. What do you mean? Yeah. I'm not sure I understand what. Oh, on this diagram here. Yeah. Push it that way, I guess. Yeah, that's how they've drawn it, hasn't it? I don't know whether that's true because it's more complicated than for me to think about it while we're in the middle of the class because it's in 3 dimensions. Remember? Okay, so much more complicated than that. All right. It is, yes. It's going into the page. What we have is a uniform magnetic field. The people in the last class said, well, how do you get a uniform magnetic field? Uh, the best thing I can say is that these ideas, we can get a uniform magnetic field. By this situation here, we could set up 2 magnets. Those magnets could be very large. In the center between them, we would have an almost uniform magnetic field. On the face of this planet, it's not going to be perfectly uniform, no. But we're going to assume for the purposes of simplification in this course that the magnetic field is perfectly uniform. It is the same all the way across, doesn't matter where you are in here. In this situation, in this diagram, the magnetic field is directed into the page. And so if I were drawing these crosses, I'd be drawing the crosses green and into the board like this. You'll notice that there's also a current carrying wire in the center here. I drew it in the color I've been drawing them lately, which is orange. It's made of copper. And that current in that wire is going into the board. Also, have a look at the magnetic field that results because of that current carrying wire. It happens to be around that current carrying wire. And what they've drawn, yeah, circular around it. As we described before, the orientation that you would say, how you would describe the orientation of the wire compared to that magnetic field into the board is that they are parallel to each other. The wire and the external field are parallel to each other. When they're parallel to each other, this wire and that magnetic field, the magnetic field created by that wire can coexist in space without interacting with the external magnetic field. because those two fields can interact with each other, sorry, will not interact with each other, we have no force on that current carrying wire. The wire goes nowhere. There is no force on the wire. Let's have a look at magnetic field strength. The force on a current carrying wire is proportional to, what do you think it's proportional to? Yes. The what? The length of the wire, yes. Uh, the current in the wire, yes. The radius, in, indirectly, yes, the radius, because the larger the radius, the greater current it will be able to carry. So, length of the wire and the current. So, uh, actually, it's proportional to the magnetic field also. So, if you have a look at this diagram here, I draw a current carrying wire and then I draw it inside a magnetic field. Okay, I'll give it some direction. I'll give it a current, some direction, and I'll draw, there's the direction of the current, I. There's a force on that wire, of course. The force on the wire has to do with, of course, the part of the wire that's in the magnetic field only. So the length of the wire, we call that delta L. This is the current element. It matters with the, yes, proportional to the current and the strength of the magnetic field. The force is equal to I current times the current element times the magnetic field. And that's assuming that this wire is perpendicular to the magnetic field. Of course, if I rotate the wire around to parallel to the magnetic field, what force is there on that wire? Zero force on that wire. So I'm not going, so in between zero force and right around to maximum force, there's a varying force all the way through. The angle matters, yes. It is sine theta, I'll show you why. Yeah, they call the length of the wire inside the magnetic field the current element. Current element is delta L. It's the current element is the length of the wire that is inside the magnetic field. Why they call it the current element, to tell you the truth, I'm not sure. It's the element that is inside the magnetic field. Here's a situation where we have a magnetic field. I'll give it direction up the page again. I don't know why. Up the page. And I'm going to draw a current carrying wire in that magnetic field. And if I draw it that way, you know that it's going to experience a force. If I draw it that way, you know that it won't experience a force. Okay? Oops. And if I then draw it that way, then there's going to be a force, but it's not as strong as if it were perpendicular to the magnetic field. Let's do that then. There's our current carrying wire. Actually, I won't draw an arrow on that. I'll just draw a current. There's my current. That doesn't matter so much for now for this explanation. You can see that, yes, current element is this distance here between the two white dots, delta L. Okay, so where will I put that? Okay, it's delta L is the portion of wire that is inside the magnetic field, yes. We know that if the wire were perpendicular to the magnetic field, that the force on that wire would be F equal I delta L B. And we know that if the wire is parallel to the magnetic field, that F is equal to 0. There is no force. The two magnetic fields, the external magnetic field and the magnetic field that results because of this wire. And remember what it looks like. It looks something like this. Okay. I'm not going to draw its direction, but it's around the wire, something like that. Okay. The magnetic field due to this wire and the magnetic field, this external magnetic field to that wire, interact with each other. I'll just remove those now just to keep this diagram as simple as possible. Have a look at I'm going to break up this wire into its two components. What I've done is I've taken this current element delta L and I've broken it up into its two components. Let's just show that they are components. Oh, okay. Which component do you think interacts with the magnetic field? Yeah, the one that's perpendicular to it. So this component of that current element here, the vertical component that we see here, we could say that it's actually the component that is parallel to the magnetic field and therefore doesn't interact with the magnetic field. But this component does. Okay, so I want to know what the component here is in order to calculate the force on that current carrying wire. And here's how I do it. I have to know the angle, theta. And if I know theta, like Paul said earlier, it's sine theta opposite over hypotenuse. Okay? The component of the current element that is parallel to the magnetic field does not interact. The component that is perpendicular to the it's the field. It's an external field. I'll just say the field experiences a force. It's okay. We can stop there today.